Hi, everyone. Hope you had a nice winter break and also a new year. We're going to get back to this chase with basically the videos that we've been making. And today we're talking about consciousness and the collapse of the wave function. Now, this is going to be the first video out of a two-video series, basically covering this paper because it's quite lengthy. What it discusses in more detail is if the wave function that describes quantum mechanical systems is potentially collapsed by the presence of consciousness and what that would then mean. This is a vague formulation at this level, and it's kind of hard saying, what is consciousness to begin with, because it's a concept we don't quite understand. And then it's also sort of a narrative that's been pushed historically, but is not as popular anymore. Nevertheless, David Chalmers makes an active attempt in taking this framework and then also developing a sort of model that's as competitive as can be to evaluate basically if this way of approaching the problem is fruitful and if that's actually a promising way forward in terms of just research in general. So with that said, we're going to jump into this. So the big picture of what we're trying to do is we're trying to discover whether the wave function is collapsed by consciousness. And this idea then was taken very seriously by von Neumann and other researchers, but today is quite widely dismissed. And the reason for that is largely how vague the concept of consciousness is. We cannot fully specify it and give an accurate account for what it is and how it affects other systems. And so trying to make a scientific theory based on consciousness is hard for that sake. But this paper combines a mathematical theory of consciousness, which is IIT, the one they're using. We've made another video on that, so we're not going to go into IIT in detail. So please check that out if you haven't seen it. And then with this mathematical model, they combine that with an account of quantum collapse dynamics. So we're going to go into, in just a second, quantum mechanics in more detail. But the high level of quantum mechanics is that any given particle or anything in general is generally before a measurement found in a superposition of states, and when you measure it, it falls back to one of the particular states that it could theoretically be in. And so the quantum collapse dynamics is the dynamics that describe how those things collapse into concrete states, let's say. So a simple version of the theory is falsified by something called the quantum zero effect, but more complex versions remain compatible with empirical evidence. So that is sort of the conclusion. They find both, let's say, promising results within this paper, but also setbacks and things that are challenges for this sort of methodology. And in principle, versions of the theory can be tested in quantum computers, and they find that the field is worth of further exploration. So to begin, I think it's most natural to begin with some quantum mechanics and basically quantum collapse dynamics. And a very famous experiment of this is something called the double slit experiment, which we can see here. What it does, or the high level interpretation of this experiment, is that you have an electron beam gun here. So this shoots individual electrons through a double slit like this. So this is a plate or something, that blocks the electrons in general, but you have two slits or openings along this. And then you have a detector on the other side. And what this experiment aims to figure out is basically whether the electrons behave like particles or whether they behave like waves. So in quantum mechanics, there's this notion of, let's say, a wave duality of everything. So quantum mechanical systems are generally described by something called the wave function, and you can generally describe then any systems of particles by means of a wave. But from Newtonian mechanics and sort of the higher level that we're used to dealing with for larger scale physics, we think of things as objects, right? So if you have an electron, you would kind of think of that as some small marble or something of the sort, kind of like what is indicated in the figure here, right? We have some small beams being shot here, but they're also waves as per the current interpretation of quantum mechanics. So depending then on if the electron would be a particle or a wave, you would see some different phenomena here. You would, to begin with then, if it was a particle, you would expect to see two slits on the detector, because you shoot these through and most of them get sort of blocked, but for a few of them, they would make it through the slits, and you would see basically a mirroring of the slits on the screen back here. But that would not be the case if the electrons were waves. So if the electron was instead a wave as opposed to a particle, if you shoot an array of waves like this, you could imagine what happens when you have waves coming up to let's say a slit in a shore. You would have on each of the slits, you would have like circular waves coming out from them, and then you would get from those an inference pattern on the screen here. If you're a bit unfamiliar with that inference pattern, I would definitely check out looking into this double slit experiment in more detail. It's, if you're going to go through all the details, it's going to be a bit lengthy, but if it's a wave, the waves would interact, and then what you would see back here is a pattern just like this. So the experiment here indicates at first sight that electrons are a wave. But if you just shoot one electron, that's a cool part about this experiment. If you just shoot one electron, you would always find a particular point here where it hits the screen. So it's neither, it seems, neither a particle or a wave, or both, I guess you could say. So that's the wave-particle duality in quantum mechanics. So it behaves both like a particle, so when you measure it, it has a distinct position, but before you measure it, that particular one, you get an inference pattern like this if you just shoot an array of electron. So what this experiment actually indicates is that the electrons exist in a superposed state until they're being measured. And when they are being measured, they collapse into one of the allowed states, let's say, that you could have for a particular electron. So it's a very interesting experiment, and it had researchers, and still has researchers, baffled about why this actually occurs. So as far as predicting just empirically what's going to happen in a given scenario, current quantum mechanics does a pretty good job of that. But actually answering the question of what happens here and what brings about this behavior is something very different, and something that still has researchers arguing about, what the actual cause is. Okay, so to make a slide then about measurement in quantum mechanics, because this is really getting to the core of what we're trying to solve here. We're trying to see if this collapse that we just saw in the previous experiment would have anything to do with consciousness, because we noticed that, it's only when we measure these particles directly that we see them turn into one given particle and fall into this particular state and lose their sort of superimposed state that they had before. So that's where we want to look into more detail and see if we can come up with a theory that describes how consciousness would bring about that effect. So it's widely accepted, I would say, in the research community, that quantum mechanical systems are described by the wave function. So the wave function is what would give rise to an inference pattern like we saw in the previous experiment. And that is, let's say, taken as true within the scientific community. And the wave function may assign a superposition of multiple values for position, momentum, and other properties for a given particle, let's say. So it doesn't exist in one of them. And that's exactly what we saw in the previous slide and in the experiment. And the wave function is then driven by two separate principles. So in time, the wave function, let's say, evolves according to the Schrodinger equation. So it's perhaps the most famous equation in physics, and you can see it down here to the bottom right, and it describes how the wave function develops through time. And it's linear, deterministic, and constantly ongoing. So that's the one part of this picture. But then also, there is a process of collapse into a definite state, which is nonlinear, non-deterministic, and happens only on certain occasions of measurement. So this does not normally happen to a system, but when you actually measure the system, that happens. And that seems very suspicious to, at first glance. Okay, and the above, so the things that we discussed here about the Schrodinger equation and then the collapse are accepted as, for empirical predictions. They predict things in a very good manner, and there's not a lot of disputes about whether or not they actually do the right, or whether or not you actually get the right thing out when you compute according to this. But they're less popular when it comes to the underlying physical reality and what actually happens to describe this process. And so you have a number of problems. Perhaps the most central one that stares you right in the face is the measurement problem, which is that collapse happens when and only when you measure the system. And this is, measure the system to begin with. It's a very vague notion, and it's very problematic because what does measure the system even mean? Let's say you have some sort of measurement device, and you could, that does a measurement, but no one would ever figure it out. Would the result actually be the same? it seems, you can do experiments where you don't look at it when you do the measurement and then come back and see that, okay, this happened, but that's not really where you're getting to, right? Because then at the end you are doing a measurement. So no one really knows the answer to that question. And that's one thing we're now trying to describe with a connotation of, or with a more rigorous definition of what consciousness could be. So we want to cut the notion of a measurement out from a physics formulation because it doesn't really do anything good to us in terms of creating a predictable set or creating a better understanding of reality, because we don't have a clear definition of what consciousness is. And so in order to use that as a scientific term in a scientific setting, we would want to know the details of what that constitutes exactly. So yeah, we want to specify that process more clearly. The second thing that very much cuts into this, and something we also made a video about a while back, is the mind-body problem. So the mind-body problem is a famous philosophical problem originally posted by Descartes that talks about the interaction between your physical body and also your mind. So what is the relation between those two and how do they interact with each other? So as a definition of what consciousness is throughout this paper, they're saying that something is conscious when it is like something to be that particular system. And the same thing goes for a mental state then. So the mental state would be conscious when there was something to be like that mental state. And one very central question to the mind-body problem is, why do physical processes give rise to consciousness at all? So popular these days with the expansive scientific theories that we have is the materialist view, which is that everything is physical and there's no, let's say, additional contribution required for consciousness. But at the same time, if that's the case, it's kind of strange and no one really has a clear answer to why do the physical processes manifest themselves in such a way that we get phenomenological experiences, so that we feel things and experience things ourselves. And why also then does consciousness and something you perceive play a causal role in the physical world? These are very central questions, and we're not going to go into the details of all the different ways people try to explain this problem. We have, as I said, a separate video on that, so please check it out. But that is also getting to the heart, really, of what we're doing here. Because if we're developing a model of consciousness that also predicts, well, the measurements that we're seeing on the quantum mechanical side, that will be strong justification for a way forward with the mind-body problem too. The question we want to ask ourselves next is, could consciousness, and in that case, how could consciousness cause the collapse of the wave function? So saying that it is an act of consciousness, just like we stated before, is quite intriguing because it would solve our two problems at once. It would basically solve the problem that consciousness brings about the wave function collapse, and it would also solve the consciousness causation problem, like we discussed in the mind-body problem slide. And so it would provide an interpretation of quantum mechanics that accepts the standard measurement collapse principle, which, as we said, is there's kind of there's a lot of dispute about currently within the scientific community what actually happens when we measure this. And it provides one of few non-arbitrary criteria for what measurement is and when it occurs. And perhaps then, if this avenue seems fruitful, then our concept of measurement might only be that it's measurement by a conscious observer. And that would leave us in a better position to scientifically describe quantum mechanics and also gain an understanding for what happens when we have these kinds of collapsing criteria. It still leaves sort of the open point of what does it actually mean for something to be a conscious observer, but at least it's a narrowing down of just measurement, which is the current, let's say, criteria for the collapse. So the reason why this is not a very popular view, so when we say this, we refer to the collapse of the wave function as a consequence of consciousness, is that it's partially popular among unscientific circles and is frequently discarded on the basis of imprecision and dualism. So imprecision is because we don't know exactly what consciousness is and how to describe it. And dualism is that you're sort of inferring. It's hard to state this while maintaining a materialist view, which is very much what the scientific community gravitates towards because of the recent successes, I would say, for the last couple of 100 years by sticking to that materialistic view. So, maybe that's the right view as well. The paper doesn't necessarily argue that this is the correct view, but it puts it forth as a viable alternative. And I think it needs to be considered with, it needs to be adequately considered. And the view seems to accept consciousness from the standard quantum mechanical laws governing physical systems. So this, is very similar to just saying dualism. So we seem to have different properties for consciousness and then also for just the physical world. And they seem to be sort of non-compatible with each other. And if you want to describe the universe in as simple of terms as possible, that is not a very good approach to take because it also introduces a lot of complexity. And generally, complexity is a bad thing. Like if you can describe something with lower complexity, that's definitely better than describing something with a lot of complexity. That's the reason why we're, for example, saying that the Earth gravitates toward the sun or around the sun. Technically, it could be the other way around, that the sun gravitates around the Earth. But if you stick to that notion, you would basically have to do adjustments for pretty much everything in the universe because everything that we see indicates or that smaller objects would revolve around bigger objects in the solar systems. There's no one saying that that's actually the most fundamental of reality that you have. But in the same sense, if you were to describe it in another way, you would have to justify a lot of strange effects that you don't have with the current framework. And that's generally how you devise a good scientific theory. Sometimes you can upfront disprove the theory and say that this is not correct because we have some sort of because things don't add up. We have a contradiction in our theory, and in that case, you can discard it. But most of the time, or some of the time, you don't have something as clear cut, but then explaining something usually comes down to explaining it in as simple terms as possible. And that's why this is not generally a theory that's embraced by the scientific community, because it's adding a lot of complexity that you haven't had to add recently in order to describe systems, and you would need some exceptional motivation why that should be required in a case like this. So it's not, let's say, the first option to do such a radical change in theory. So that's why, there's some argumentation about whether or not this could be a valuable way forward. But if we take it as a viable way of describing the quantum mechanical collapse, you could do it in a few different ways, specifically two that they bring up in this paper. And it describes the locus, which is, let's say, the focal point of collapse for the quantum mechanical system. And if we start with a variable locus, that's closest to our standard view of quantum mechanics. What a model like that would say is that many different observable quantities can be measured and thereby serve as the locus of collapse. So you would have, for example, position, momentum, mass, and spin. They would all be different and they could all bring about collapse in different ways. And the wave function then collapses upon measurement with probabilities according to the Born rule. So if you're not very familiar with quantum mechanics, the Born rule might sound, unfamiliar, but really it just describes what happens usually in a quantum mechanical setting when state collapses. So that is already something that's part of the empirical, let's say, verifiable part of quantum mechanics that people agree on. Like the Born rule describes how these superimposed states collapse onto, the concrete ones, and with the probabilities that it does so. On the other hand, you could also have a fixed locus, which says that, let's say, consciousness itself or its physical correlate, whatever it is, but one quantity serves as the locus of collapse. And it always does that. And that could be then developed with special superposition resistant observables, which resist superposition then. So you have some system that normally goes into superposition, but with these particular observables, they would resist that. So they would basically try and stay in a particular state and not go into superposition. And then it would cause the entire system to collapse as a consequence. And the fixed locus models are simpler. They limit complexity. And much for that reason, those are the ones that they move forward with in this paper. So going forward, we're going to consider the fixed locus models. The next thing that we need to look into in more detail is this super resistance. So we mentioned it here, superposition resistant observables, which we just for short say super resistant. It works well with the measurement collapse interpretations of quantum mechanics, as we said before, and it's the most simple approach would be to assume that consciousness is absolutely super resistant. So whenever consciousness interacts with the system, that would cause it to collapse and fall into one of the measurable observable states, let's say. And that seems good and all, but it leads to one fatal problem for absolute super resistance. And that has to do with things changing their state. So we're going to get to that in just a second, but just for now, this would be sort of the preferred approach, but here's where they're actually experiencing a problem with a model. So you would think of these super resistant properties as measurement properties. So one example of that would be your conscious experiment, and not as a measured property. So not a particle position, for example. So the difference between these is like the measurement property would be something like an indicator on an oscilloscope, for example, but it would not be the particle's position itself. So those, the dial on the oscilloscope, that would be the measurement property, and that would be the super resistant one. So that's the one that doesn't want to go into superposition. So we're giving an example of this here, and you think of, well, this is the reason why I brought up oscilloscopes. So you think of some measurement devices, oscilloscopes, and they have measurement properties. So those are the meter readings or point locations or whatever it might be on the measurement device. And they resist superposition and tend to collapse. So when you measure something with the oscilloscope, a measurement property, so that would be the position of the atom or whatever you're trying to measure, would affect the measurement property, which is the dial on the oscilloscope. And if we suppose that we have a quantum system, so a particle in a superposition, then that would be, let's say, a mix-up between state A and state B. So when you have a superposition, you have a particle that's in two states at once, and it only collapses to one of them when you actually measure it. And if it wasn't for this principle, the particle would yield an entangled superposition. So as we can see described here, where M of A and M of B are the states of the measurement system. So that would be your oscilloscope. So what we're saying here is basically that the dial would be in a superposition of, well, let's say you have a dial that only can be on or off, like a switch. So it would be in a superposition of on and off. So it would be both on and off at the same time. And that's obviously not what we're seeing when we're measuring an oscilloscope. So something here seems a bit strange. But because now M is super resistant, the particle and measurement system will instead collapse into either A M of A or B M of B. So it would not be in this superposition, but it would fall down into one of them because the dial itself resists being in superposition. So this seems good, but here, and it's also then compatible with a materialist and dualist views. So the materialist view would be simpler here. You would just say, yeah, basically these dials, whatever it is, fall into place or resist the superposition and therefore keep to their specific places. And the dualist view, on the contrary, would say that the subject will only be in a certain state of consciousness if it is in the corresponding physical correlates of consciousness. There is, however, a big problem with this, a fatal problem, as it turns out. And that is that this superposition resistant dial, in this case on the oscilloscope, would never actually be able to switch. So if we're looking at the dynamics of the system, when we're saying that this is superposition resistant, you're saying that it would always be in one of these states. So the dial always keeps to one of these and never, belongs to an intermittent stage where it's a function of both. And that's a problem because in the quantum mechanical world, the way particles and systems change their state is by changing the weights in their superposition. So if you have a system where it always falls into, let's say, the A state, that would basically mean that this part is weight to 100% and this one basically gets 0%. And as these partially transition, this one gets more and more of the weight until you get to the point where it always collapses into B. And that's basically how you would switch from two states if you go from one very deterministic one to another. But there's a problem if we always have this approach, which is that if you're always in one of these states, how are you going to change gradually the weights of the superposition so that you can fall into the other state? Another way of putting it is, how would you ever switch from A, M of A, to B, M of B? It doesn't really work. It doesn't work according to the laws of quantum mechanical systems as we know them today. So if you impose this framework, it leaves a critical problem, which is that the dials of this oscilloscope would never actually be able to switch. So they would be off for eternity, let's say. It's not a very good, I mean, it's not a very good conclusion for this sort of simple model of super resistance. And we see here that, okay, something needs to happen. We can't have something that's always absolutely super resistant and can never go into a state like this where it's a mix-up between two states, because then it can never change. So what we turn to next, so now that we basically failed with this simple model where we're trying to explain consciousness is something that absolutely resists superposition, we're left at, let's say, a point where we need to either make our model more complex or discard this theory altogether. And what we're going to look into for the next video, so that's not going to be in this one, but what we're going to continue next time is developing a framework that treats consciousness as super resistant, but not absolutely super resistant. So here on, in today's video, we basically said that super resistance that we have for consciousness is absolute, and that any conscious system can never be in a superposed state. What we're going to say in the next video is basically we're going to relax that assumption somewhat and say that, okay, for this given state, we allow it to actually be in a superposition for some amount of time, but it's generally going to fall into the category of not being in superposition. So it's going to have some sort of tendency to fall back onto things that are deterministic and where we actually have one state. That would allow us to basically, for a short amount of time, have a superimposed state like this where we can change from the A state to the B state, for example. That would solve our dial problem and potentially also give us a firm and then conclusive model of how consciousness would interact with quantum mechanics, and give us a full set of dynamics for how this interaction works. So that's where we're going to stop for today. Thanks a lot for watching this one. Make sure to check out the next video, which we're going to publish in a week from now. Thank you very much for watching, and see you in the next one.